Hi guys, welcome back. In today's video, I'm going to talk about electromagnetic interference and how to deal with it. So when you're surrounded by different equipments connected to the power grid, your body acts like an antenna and the noise is superposed to your own biopotentials, disrupting the quality of the signal. So a way of dealing with that is to use a band stop filter. So here I have a notch filter. A notch filter is essentially a band stop filter with a very narrow bandwidth. So this is called a 20 notch filter. And here I am rejecting 53 Hertz. This, for those who've watched part 1 of the video, that's a minimalistic circuit of my EMG. And this is the same thing, but with the notch filter. And as you can see here on the plot, here's my unfiltered and here's the filtered thing. And here you can clearly see that at around 53 Hertz, I have this very strong attenuation going on. It removes the unwanted frequency, but at the same time, it creates a really strong attenuation on our differential signal. There is another method which is called active grounding or driven right leg, which affects only the common mode signal, leaving our differential mode completely unaffected. So right now I'm going to show you the theory behind the driven right leg. So here we're going to start with the common mode. If you have a common mode signal across here and here, given the principle behind an operational amplifier in linear mode, the potential here is equal to the potential here. So if you have VCM here, you have VCM here as well. And there is nothing here, so the potential here and here are the same. So you have VCM here, and for the same reason, you have VCM here. Since you have the same potential across here and here, you have no current flowing through this entire part of the circuit. So it's VCM everywhere. So here it's VCM, and here you have the VCM as well. So we can clearly see that the common mode signal is not amplified. Now, if we look at it from a differential standpoint, let's say we have V2 here, and here we have V1. And this is our V differential. So for the same reason, here we're going to have V2, and here we're going to have V1. Here we're going to have V output 2 and V output 1. Now, if we want to define the values of VO2 and VO1, you can do it in the way you want. I like to use Millman, but I'm not going to apply Millman here because I don't know what's the potential here and here. So I'm going to place myself where I know all the potentials. So I'm going to place myself here. So we only deal with the red color. We are in the differential mode right now. So the potential here at V2 will be VO2 over this resistance and V1 over R1. So here's it. Here it is here. VO2 over R2, V1 over R1 over the resistance, and you do the same thing placing yourself at V1, and you have VO1 over R2 and all this. So from here you just subtract to have your differential signal. It's just this minus this, and then you multiply everything by the denominator to simplify things a little bit. And here you can see that we have V1 minus V2, which is minus VD. And by rearranging things, you end up having this expression, which is the value, the difference in potential across this part of the circuit. So VO2 minus VO1 is equal to the V differential times this gain. Now we've seen that the VCM is not amplified, so the potential here, if you look at it, another expression, VCM is the average between the two potentials. So it's V1 plus V2 divided by 2, and here is a V differential. By rearranging things, you end up having VCM minus V differential over 2, V1 equals that, and V2 equals VCM plus VD divided by 2. So this V2 is the superposition of the common mode and the differential divided by 2, and here V1 is the superposition of this minus VD divided by 2. And as a result, this VO2 is going to be this one times our gain, and VO1 is going to be this, since the VCM is not amplified. And if you do the difference between this whole expression, you end up having this. Now, if we get into a driven right leg, let's place two resistance here, RD. The potential here is the same as here, so we still have our VO1 here and VO2 here. So what's happening is, if you apply at this single point here, you only have VCM, because these two, they neutralize each other, so you just end up having VCM across this conductor here. So here you have VCM, and that's really interesting for us because we just have the common mode. So we are not dealing with the differential anymore. And if we place a non-inverting op-amp here, let's call it our feedback, what happens is, since the potential here is 0, that's ground, the potential here will be 0 as well. So here we'll have VCM, and here we'll have ground, which is, we have different potentials, so there's a current that's going to flow. And since we know that input current here, the current here is going to be VCM over RD, and the current here is also going to be VCM over RD. And the total current is going to be, the sum. So I equals 2 VCM over RD, which means that VCM equals RD divided by 2 times I. So even though these resistance are, they seem to be in series, they are actually in parallel. So here we have RD, so this is our equivalent circuit. So the gain here is simply RF divided by RD over 2. That's a classic non-inverting op-amp. Now, what we are actually doing is we are creating a negative feedback loop. So here is our gain, the gain of this. Here's a negative, positive. So let's call this here the input common mode, and here is our output common mode. And here's the error. So our output common mode, the error is equal to VICM, this one, minus V output common mode times our gain. And here the VO common mode is equal to E, the error, times the gain. But we've seen that the common mode is not amplified, so the gain is 1. So VOCM equals E, simply E. So by rearranging these equations, we end up having this, and at the end we have V output common mode over V input common mode equals 1 plus 1 over G, which is an attenuation. So by looping, by having this inverting op-amp and sending the output back into the body, what we are doing is we are creating an attenuation on the common mode signal. Now, despite the fact that, even if you have an operational amplifier with a very good common mode rejection ratio, which is the ability of an op-amp to suppress the common mode noise, when you are in a very noisy environment, the inherent common mode rejection ratio of that op-amp is not enough. So you have to go through, this kind of circuit to attenuate the common mode even further. Now, spoiler alert, on my design specifically, I'm not saying it's not working universally. This thing does not work. I don't know why when I'm placing the resistance like that, it does not work unless I add a capacitor here, creating a low pass, an active low pass filter. And with this capacitor, since I want to reject the 50 to 60 hertz, I have a cutoff frequency of 80 or 90 hertz. Yeah, I have something like that. And if cutoff frequency of around this value, so the 50 to 60 are definitely rejected as well, since I'm going up to 80. So yeah, you can choose anything, something like 80 hertz, 100 hertz, whatever, but just don't choose the exact value you want to reject, because you always have to add a little bit more, because of at the cutoff frequency you already are minus 3 dB, so you have to take that into consideration. So here we have the cutoff frequency of this one times the capacitor. So if you take something like this to, I don't know, 100 hertz, it will do the job to reject the unwanted frequency. And when I have my capacitor, I have significantly better results. And I'm going to talk about that, in the final video, which is going to be a demonstration video like video number 3. So hope you learn a few things with this, and see you soon. Bye.